All right, in this lesson we're going to be looking at section 10.2, basic combinatorics. In the last lesson, we started learning how to count outcomes in an event without having to physically count each one using the fundamental counting principle. Okay, so we're going to continue that process. Let me get it focused here a little bit better. We also learned that the number of permutations, the permutations where order matters, of n objects is n factorial. That is n times n minus 1 all the way down to 3 times 2 times 1. So now I ask the question, what if the objects in the set are not distinguishable from one another? Okay, what if I have two identical things? Okay, so in that sense, I have a little process I'm going to follow with you. So go back and think about when we did the A, B, C, and we ordered those up and arranged those. Well, what if I have A, B, B? So I have, instead of, I have two B's that are indistinguishable from each other. How does this change? How many ways can I arrange these three letters? Okay, well, it's to arrange the three letters is exactly the same. Because these are different objects, I'm going to put little subscripts on it so you can see that they are different. But in reality, they're not there. So let's look and see what happens. So what I did is I did exactly the same thing we did before with C. Okay, I put subscripts on the B's so you can see that they are different B's as I go through this process. Here's all the ways that we can write those out with subscripts. So we have, what, 6 of them. But because I put the subscripts on to distinguish the B's apart, in reality, there is no subscripts. So if I take them off, then this becomes this right here. And you'll notice that I just have repeats. Okay? That repeats. This one and that one repeats. These two repeat. And so they're indistinguishable from each other. So in reality, if I only count it as one time, these 6 become these 3, and there are 3 distinguishable permutations. Okay, so we have to take that into consideration if I have repeated objects. And with that, gives you this right here. So remember, if I have n objects that are all different in a set, then the number of permutations is n factorial. But if I have repeated values, as in this example here, then I need to condense that down into distinguishable permutations. I got a set of n objects. The first object, okay, it happens that many times. Another object happens that many times, and so forth and so on. So that each of these things adds up to become the entire set. The number of distinguishable permutations of n objects is this formula right here, where I take n factorial and then divide it by the factorial of the number of times each object occurs. Now, this doesn't make sense right now. It will in the example I'm going to show you real quick. So, here's the word banana. Okay, I have all those letters. How many distinguishable ways can I rearrange those letters? Okay, how many distinguishable permutations does it have? Okay, so let me show you how that's done. Using that formula up there, the first thing I'd want to do is identify. So there's 1, 2, 3, 4, 5, 6 letters. So I know that n is going to be equal to 6. Each of these up here, each letter, count how many times it occurs. So B occurs once. The A occurs 1, 2, 3 times. The N occurs twice. And if I take these numbers and add them up, I should get 6. That's what it refers to over here when we did this. Each of those counts has to add up to the original N value, and that's what we have right here. So with that, I can use my formula. So the number of distinguishable permutations of that word banana is 6 factorial divided by, and then each of these factorial. 1 factorial, 3 factorial, times 2 factorial. Okay, and so you work this out, and so we know for a fact that that's a 1. This is 3 times 2 times 1, but this is 6 times 5 times 4 times 3 factorial. So that factorial, this is a 1 times 3 factorial. These will reduce, and 2 is just simply 2. So these drop out, and I have that number divided by 2. So the end result here is 60. Okay, so there are 60 distinguishable permutations of those 6 letters. All right, so the next question then is, well, what if I have a set of n objects, but we only want to arrange a certain number of them in order? So instead of taking the entire group and rearranging them, what if I only want to take a few numbers, a few items, and arrange those? What is that called? Okay, and so that becomes this, and I'll just show you the formula right now. This is called a permutation of n objects taken r at a time. And we write it and designate it by this symbol right here. NPR is one of them. There's another one, but this is the one we're mainly going to use. Okay, and what does this become? What formula? See, there's that n factorial again, because it's a permutation where order matters. And then we just divide it by the difference of these. So how many objects basically are left? So n minus r. R is the number that you want to take into the group. Right? This is just telling you that it's going to have 0 if r is bigger than n. You can't take more than the actual group has. So let's look at an example of this right here. I have a classroom of 20 students. How many ways can we line up 5 students? So what I have to do is I have to figure out how many groups of 5 I can create from the class of 20, and then how many ways can I line them up at the door. And that's what that formula does for you. So here, n is 20, r is 5. So 20 PR equals 20 factorial, and then 20 minus 5 factorial. And so then you can use your calculator on this. Let me show you where it is on the calculator. Get a new page here. So if I want to type that in, okay, I'm going to start with a fraction. And on top, I'm going to type 20. And you can find the factorial in 2 locations. One is in the menu button on your calculator. If I push menu, and down here you see where it says probability. So go down to number 5. And the very first one here is called factorial. So you select that, and it'll put a factorial symbol on the 20. 20 minus 5 is 15, so this is going to be 15. And then the other place I can find the factorial is down here in this button. I click on that. You get a bunch of symbols, and the second one over right there is the exclamation point. You can select that, and it'll put the exclamation point in there too. So whichever one works for you. Okay. Once you have it typed in there, hit enter, and it'll give you the number that you have. So that is the number for this problem. 1860480. So you can see it's about 1,860,000 ways I can line up 5 students out of 20. And so that's how that works. Now, let's look at this right here. Here's another way to look at the same thing I wanted to show you. This is using it as a permutation of 5 objects, okay? This right here is looking at it from the counting principle. It's the same thing, okay? I have 5, there's 20 students in the class. I want to take 5 of them, okay? So I'm going to have 5 spots at the door, or line it up. There are 20 students available for the first slot. But once I do the first person there, then there's only 19 students left to choose for the second, and so forth and so on. So you can see that I get, this right here is basically 20 factorial down to 15 factorial, which will then cancel there. So right here, after this will be times 15 factorial, which cancels with that one on the bottom. So it's the same exact process. So I use this quite often, and but you can also use this up here. It's the same thing. Okay. So that's just a piece of information for you. Now the question becomes this. What if we don't need to count the number of ways to order our objects taken from a set of n objects, but we want to know just how many different groups of our objects can be made, where order doesn't matter, okay? Some examples where this occurs in real life, the lottery. Everybody's familiar with this California State Lottery. They have those little ping pong balls in the machine. They do it all up and the numbers come out at random things. But the order in which those numbers are does not matter. You don't have to have the numbers in the exact same order that they came out of the machine. If you just have those numbers, then you're a winner. If I want to pick a committee of people, okay, there's no order to this thing. If I'm doing a pick for a team, if you do like when you're in grade school and you pick teams and you just did one person at a time. If you're on the team, you're on the team. Okay. And another one where this is used quite often is in poker hands, card games, things like that, because once I get dealt a bunch of cards, I can put them in any order that I want. So order, again, does not matter. So in that situation, what do we have there? That is called a combination of n objects taken r at a time. So again, combination means order does not matter. Permutations mean order matters. This is how you tell which one to use. So here's our formula. It looks very similar. Okay, so if I look at that right there, that's the NPR. But for the NCR, because order doesn't matter, I'm dividing because I'm eliminating those ones that have the same group, that are in the same group. So this is NCR, and this is our formula here. So how do I use this? What does it look like in real problem-solving techniques? So here's our class. I'll just move it over here so you can see what I've made over here. So I have a class of 20 students. I'm going to select 4 students at random. So how many groups of 4 can I create out of 20? So because order doesn't matter, I can see that order does not matter here. Then I know that it's going to be 20, C, and then a 4. So using our formula, I know I'm going to have 20 factorial, then a 4 factorial, and then a 20 minus 4 factorial. Or simply, and then this is 4 factorial and 16 factorial. Now, I don't expect you to do this by hand, but this is what it would look like. See, this is 16 factorial and 20, so then on top it'd be 20, 19, 18, 17. The next one over is 16 factorial. On the bottom, I have 4 times 3 times 2 times 1, and then 16 factorial. And these just simply drop it out. So this is all that I have left. And if you work that out, you're going to get 4,845. Now, this is working it out by hand. This over here, we typed in this fraction. Let me show you how I can get both of these answers on the calculator without having to type it in individually. These are built-in templates into your calculator. When you do your work for me, you have to write this, you have to write this, okay? And then you can write the answer. You have to write this, you can write this or this. Either one of these two is fine. And then you can write your answer. You don't need to do it by hand. Here's how it looks on the calculator and where you go. So let's go back up to this one, the NPR. Let me get the glare out of there. Okay. So what you do is you type in the menu button and go down to probability number 5. And when I go over, the first one is factorial, but the second one is permutations. Okay. That permutation is this one right here. Okay. That's what they mean by that. And so if you select that one, you're going to get NPR, and then you're going to get a parenthesis. In the parentheses, you need to type 20, and then you need to type the comma, and then you need to type the 5. So that means 20D5. And when you hit enter, you get the exact same answers we had before. Okay? Same thing for this one down here. Menu, probability, and number 3 is combination. And it's done the same way. You have to type in 20, comma 4. And there's your 48, 45. Okay, so that's how you can use the calculator to assist you with that. All right. The next one is the thing about subsets. So I'm going to talk about this, and then I'm going to show you the formula where it is. So what do I mean by subsets? So here's a group of 3 objects. Okay. How many different groups can I make from that? Counting the group that has nothing in it and the group that has everything in it. So what I mean by this, and what they mean by this is, this right here is the group of nothing. I can choose nothing from here. That is counted as a subgroup. Okay. Then I can count all the singles. So there's that, there's the B, and there's the C. Oops. These are the groups of singletons. Well, then I can do groups of 2s. So there's A and B. I can do A and C. And I can do B and C. And then there's the group that uses all 3. A, B, and C. And so you can see that then I have 8 subsets of a set of 3. Okay? Including the empty set and the entire set. So the question becomes then is, how do I know how many subsets? Is this a pattern? Can I do this for all things? If I kept on going and trying different ones, would I see a pattern emerging from this? And the answer is yes, you will. And so what is that pattern? That pattern is simply this. Formula for counting subsets of a set of n objects. There are 2 to the n subsets of a set of n objects, including the empty set and the entire set. There's 3 objects in here. 2 to the 3rd is 8, and we found 8 objects, 8 subsets. So that's how that works, and that's useful because I have another example I want to show you and how that can help us in solving some of these problems out. So this one I'm just going to show you so you can see how it's done. So Luigi sells one size of pizza, but he claims that that his selection of toppings allows him to make over 4,000 different pizzas. What is the smallest number of toppings that Luigi could offer to make this happen so he doesn't get sued for false advertising? Okay, so on a pizza, I can have a pizza of just cheese. So if you count cheese as a topping, that would be 1. If you don't count, you can have a pizza that's just the bread. Okay, that's no toppings. That would be the empty set. And then all the toppings he has, you can only put 1 topping on the pizza. And then you got to go back and put in, 2 toppings on the pizzas. And then how many pizzas can I do with 3 toppings, and so forth and so on. So that's why it represents that number of subsets. And so from that, we're going to figure out what the number of toppings has to be to make it equal to 4,000. And so that would be that right there. How many subsets of toppings equals 4,000? So this is an exponential equation that we know how to solve from before. We simply just go through the process over here of taking the log base 2 of both sides. This gives me n, and the log base 2 of 4,000 is 11.966. That's where it equals 4,000. You can't have partial toppings, so you need to go to the next one up, okay? Because I have to make over 4,000, so it has to be bigger than this number here. And so the number of toppings that I can have then is 12. And so that's how that works. It allows you to solve a problem in that time, okay? So we'll do more examples together in class, and that ends this one.